Let's define a compact set. A set A in the reals is compact if every sequence in A has a subsequence that converges to a limit that is also in A. Based on this definition, what are some examples of compact sets? The most basic example is a closed interval from, say, A to B. If we have a sequence xn that lives in this interval, then it's a bounded sequence. And so the Bolzano-Weierstrass theorem guarantees that it has a subsequence that converges. And since all the terms of that subsequence are greater than or equal to A and less than or equal to B, then the limit is also greater than or equal to A and less than or equal to B by the order limit theorem. On the other hand, the open interval from A to B would not be compact, because you could construct a sequence converging to, say, B, and then any subsequence of it would also have to converge to B, but B is not in the set. In this setting of the real numbers, being compact ends up just being slightly more of a constraint than being closed. So we've defined bounded above for sets, and we've defined bounded for sequences, but we can also write down in a similar way what it means for a set to be bounded. So as a definition, we say that a set A is bounded if there exists a real number big M, such that the absolute value of A is less than or equal to big M for all A. And we can state as a theorem that a set A is compact if and only if it is closed and bounded. For the proof of this statement, let's start with the forward direction. Let A be a compact set. We need to show that A is closed and bounded, so let's start by assuming toward a contradiction that A is not bounded. This will allow us to construct a sequence that diverges toward infinity, and then no subsequence of that will be able to converge. And there's a variety of ways to detail how you might construct such a sequence, but one natural way is as follows. For each natural number n, there exists at least some specific an in our set A, such that the absolute value of an is greater than n. So we're using the fact that A is unbounded, and so each natural number can't be a bound. So we start with 1, and we say there has to be some element of the set with absolute value greater than 1. And then we go to 2, there has to be some element of the set with absolute value greater than 2, etc. And we construct this sequence. And any subsequence of this sequence an must also be unbounded, and thus not convergent, contradicting the definition of compact. So A must be bounded. Now, to show the other half of the forward direction, that A must be closed, let A be a limit point of A. Then there exists a sequence an that lives in A that converges to A. Since A is compact, there exists a subsequence of this sequence that converges to some element of A. But any subsequence of a convergent sequence has to converge to the same limit, and so it converges to A. So A is an A. Thus, A is closed. For the reverse direction, assume A is closed and bounded, and we'll now show that it's compact. Let an be a sequence whose terms are contained in A, and we'll need to find a subsequence that converges to a limit in A. Since A is bounded, the sequence an is bounded, and so by the Bolzano-Weierstrass theorem, it has a convergent subsequence, A sub nk, converging to some limit L. Since A is closed, and L is a limit point of A, L is in A. Thus, A is compact. This notion of compact as being both closed and bounded makes closed intervals, or unions of closed intervals, the prime examples that come to mind when we think about compact sets. But this isn't really a general characterization of all types of compact sets. To see a different example, consider the Cantor set. The Cantor set is actually compact. So recall this construction where we start with the interval 0 to 1 and progressively remove middle thirds from the remaining intervals and define the Cantor set to be only what's left over in this intersection of all the things that didn't get removed. This is definitely a bounded set because it's bounded between 0 and 1. And the complement of the Cantor set is a union of open intervals. and arbitrary unions of open intervals are still open. So the complement of the Cantor set is open, which means the Cantor set is also closed. Since it's closed and bounded, it's an example of a compact set. Let's recall the nested interval property that we explored in episode 4 as one of the implications of the axiom of completeness. We took a sequence of nested closed intervals, meaning each interval was contained in the prior interval, and we said that their infinite intersection is non-empty. The same result holds if we loosen the requirement on these sets from being closed intervals just to being any compact set. So it'll be a stronger result that we'll call the nested compact set property. If we have infinitely many non-empty compact sets, so if A1, A2, A3 are non-empty compact sets, such that A sub n contains A sub n plus 1 for each natural number n. In other words, this is a nested sequence. A1 contains A2, which contains A3, etc. Then the infinite intersection n equals 1 to infinity of an is non-empty. In order to prove this statement, we'll need an element that is in this infinite intersection. So it should be the limit of some sort of sequence. For each index n, let xn be an element of an. And then, because the sets are nested, this xn will also be contained in an minus 1, an minus 2, all of the prior sets. Specifically, xn is definitely contained in A1 for each n. So, by the definition of A1 being compact, the sequence of the xn has some subsequence, say x sub nk, that converges to a limit L that lives in A1. But not only does L live in A1, we could argue for any index m, L lives in AM. We could just note that the terms of the sequence x and k live in AM for all nk greater than or equal to m. This results from the fact that we chose each xnk to live in ank. And because the sets are nested, AM contains ank for any nk greater than or equal to m. So the infinite tail of our subsequence lives in AM. Ignoring the finitely many terms at the start with index less than m, the property of AM being compact guarantees that the limit of this subsequence lives in AM. But we called that limit L, so L lives in AM for each m. Therefore, L lives in the infinite intersection of the AN, proving the result. We've discussed how unions and intersections interact with open and closed sets, and when the qualities of being open or closed are preserved, and when they're not necessarily preserved. We could ask that same question about compact sets. Taking unions or intersections of compact sets, when is the result still compact? Is it only guaranteed in the finite case, or could we take countable or even uncountable unions or intersections? The result ends up being the same as it was for closed sets, that finite unions of compact sets are compact, and that arbitrary intersections of compact sets are compact. To prove each of these parts, we just need to show that the property of being bounded is preserved, because we've already shown that the property of being closed is preserved under finite unions or arbitrary intersections. Let A1 through AN be compact sets. So A1 through AN are closed and bounded by, say, M1 through Mn respectively. Taking M to be the max of M1 through Mn, M is a bound for their union, and we know their union to be closed, and so their union is compact. For the proof of the second part, let A lambda be a compact set for each lambda in lambda. Then each A lambda is closed and bounded. We can't take the max of the bounds for each A lambda, but we don't need to. We just need one specific bound. So let M be a bound for some specific A lambda prime, such that lambda prime is in lambda. We can just pick one at random. Letting A denote their arbitrary intersection, since A is a subset of A lambda prime, A is bounded by M, and A is closed because it's the intersection of a bunch of closed sets, so A is compact. To practice recognizing compact sets, let's assume that A is compact and B is closed, and decide if each of these sets are closed, compact, neither, or we don't have enough information. What about this set difference, A minus B? Well, this is all the elements that are in A that aren't in B. So this is the intersection of A with B complement, but B complement is an open set. So this could be compact, say if A was a subset of B, but this also could be open, or it could be none of closed, open, or compact. What about the intersection of A and B? This would have to be compact. It's the intersection of two closed sets, so it's closed, and we know that A is bounded, and this is a subset of A, so this set is also bounded. What about A union B? This set is going to be closed, because both of those are closed, but it's not guaranteed to be compact, so we don't have enough information to determine. It will depend on whether or not B is bounded. So far, we have two characterizations of compactness. The first one that we took as its definition, that any sequence will have a subsequence converging to its limit in the set, and the second one being that the set is closed and bounded. And we've proven that these are equivalent. But we'll also have a third characterization of compactness. In the next video, we'll state that third notion and prove that all three are equivalent in what's called the Heine-Borel theorem.